Uh, Okay, now we are recorded, which is perfect. I will mention it later. My name is Zuzana. I am delighted to be your facilitator for today's session called Opportunities and Challenges for Circular Water Management in Urban and Rural Areas. Today we are definitely diving into one of the most critical challenges for our cities and regions, the circular management of water, which is very, very important. As I mentioned in the beginning, this seminar is running under the European project called NiCE, which aims to promote sustainable lifestyles and circular production models across 8 Central European cities. The project is running from the May 2023 up to the April of this year, and we are doing those online seminars to really be focused on raising awareness. Little bit of technical information before we start. Please, if it is possible, turn off your microphones. You can have your camera on if you wish. For your questions, you can definitely use chat, or for the anonymous questions, we have also the Slido app. The link for the Slido will be in the chat. Please turn off your microphones. As I mentioned in the beginning, this session is recorded, which means that from the point of the GDPR, please, by attending this webinar, you are sharing your consent, and also this record may be shared on YouTube later on. Webinar is definitely interactive. If you have a question which you would like to express by the word, raise your hand and you will have a space to really share and express your question. And one more important thing, please use your real name attending this seminar, because you will be able to receive participation certificate afterwards, and we really need your real name to be able to do this participation certificate. Okay. So today we are joined by 3 experts from ENEA, and it is Italian National Agency for New Technologies, Energy and Sustainable Economic Development. So please first welcome our first speaker, Luigi Sciubba. Sorry for my pronunciation. I hope it's not so bad. And now the floor is yours.
Okay.
So Luigi,
good morning to all. I'm sharing my screen.
Yes.
I hope you are able to see my screen now.
Yes, it's running. The floor is yours.
Okay. Thank you, Susanna, for your introduction. I'm really pleased to have the opportunity to present here our research about opportunities and challenges for circular water management in urban and rural areas. First of all, I wish to show you a brief summary of my presentation. First of all, I will illustrate you the current framework of water management, then passing to the issue of water stress, then illustrating the possible solution of circular water management, then focusing on treated wastewater reuse, and finally concluding with some final remarks. This work is being carried out by the researcher of the Laboratory of Technologies for the Circular Management of Water and Wastewater, belonging to the Italian National Agency for New Technologies, Energy and Sustainable Economic Development, ENEA. As you can see, the name of our agency is quite complex, as it reflects the many activities we carry on. Our mission, the mission of our laboratory, is to develop eco-innovative processes and technologies for the sustainable and circular management of water resources, particularly encouraging water saving and purification treatment, valorization and reuse of municipal and industrial effluents. In this context, our research consists in the examination of the potential of water recycling and reuse, basically assessing water quality in wastewater treatment plants for agricultural reuse. As you can see in the picture, so wastewater treatment plants are our favorite places, only for work, of course. Let's have a focus. Water is the topic of this presentation, But don't worry, it is not a chemistry lesson, so I will not say you something about the bonds of water molecule. Otherwise, I will to show you the importance of water. Indeed, every human activity needs water. Water is used for home utilization, for example, personal care, clothes, clothes washing, cooking, and so on. It is used also for agricultural exploitation, for crops and green irrigation, for industrial application, such as food process in many cases, or for energy production. It is important to say that in all these activities, we use fresh water. That is water having less 1 gram per liter of dissolved salts. This is the only chemical information of this presentation you have to keep in mind. About fresh water, I want to propose you the first poll question of this presentation. I said that all human activities need fresh water, but what is the percentage of fresh water available on our planet for our activities I previously said? You can answer that this percentage is less than 1%, 3%, 32%, or about 50%. Now, you can choose the answer you consider right. Then I will explain the right one.
So maybe just my comment, please vote on the poll, which you can see on the screen. Just choose your answer, and then do not forget to submit your answer by clicking on the blue button down below. We will wait a little bit for all the answers from you. And then we will share the results on the screen.
Okay.
Okay, so now you should be able to see the results. So, Luigi, do you have some interpretation to those answers?
Okay, I'm seeing that the majority of responding people choose the right answer, as the percentage of available fresh water is less than 1%. Let's examine in detail. In fact, even if Earth is the blue planet, less than 1% of total water on our planet is fresh water available for human activities. The 97% of total water on our planet is salt water, which is in oceans and seas. So we have only 3% of fresh water. Of these 3%, the majority is trapped in ice cap and glaciers, 79%. All is represented by groundwater, more or less 20%. So the remaining percentage of available fresh water is the 1% of the 3%, that is 0.03%. And it's a small amount. Available fresh water is in soils, air, rivers, lakes, and living organisms. So the low amount of available fresh water is only one of the aspects of water stress issue. Indeed, it is accompanied by high water consumption, home, agricultural, and industrial level, as I have said. Moreover, we have to consider climate change, which causes increase of temperature and decrease of rainfalls. Moreover, there is the inadequacy of infrastructure for water transportation, also in many European regions. And finally, the contamination of surface water. All these issues causes water stress, which is mainly linked to high water consumption and low water availability. In other words, water stress could be compared to people having not much time to carry many activities that are time expensive. So people suffer stress and also water resource suffer this problem. Coming to detail, the water stress level of a certain zone could be determined by calculating water stress index. That is the ratio between the amount of extracted fresh water and one of available fresh water in a certain place, expressed as percentage by this formula. If water stress index is below 10%, we have a low stress. If this value is comprised between 10 and 20%, we have medium low stress. If it is between 20 and 40, medium high stress. If it is above 40%, the region suffers high water stress. Then, let's come to the second poll questions. With this expression of water stress expressed by the European Environmental Agency, which of these European nations, is affected by high water stress index? According to the European Environment Agency, they are all nations involved in our project, so Czechia, Slovakia, Italy, or Slovenia, according to you.
Okay, so again, you can see your choices on the screen. Now it is multiple choice poll, so you can choose more than one. Then please, again, do not forget to submit your answer by clicking on the blue button down below. A little bit more of voting. People are thinking about the right answer. Take your time, think wisely, and then we will share the results. Okay, so now you should be able to see the results on the screen. So what is the right answer?
Okay, the majority of our participants are aware that Italy has the higher water stress index, unfortunately for us. Why we have this situation in Italy? Mainly, the consumption habit of European citizens is similar regardless of the country. To have an idea, the average daily consumption of an European citizen is 150 liters per day, with no many differences between different countries. However, Italy and other Mediterranean countries are mainly subjected to water stress due to their climate. Central and Northern European nations are affected by this problem at a lesser extent. In fact, Mediterranean islands such as Cyprus or Malta suffer high water stress. Bigger Mediterranean nations such as Spain or Italy had a medium high stress. A medium low stress is the one characterizing oceanic nations such as France or Portugal, while Central and Northern European nations such as the Netherlands, Sweden, or Slovakia have low water stress index. However, all European nations should face this problem in a certain way. Therefore, action to tackle water stress are needed. There is the need to introduce measures to ensure water supply, also to address the growing distortion between seasonal variation in demand and seasonal variation in water availability due to climate change. How we can face water stress? First of all, we can work on water demand management by reducing losses in water distribution system through wastefulness reduction and improving water use efficiency by proper technological innovation toward zero discharge. We can work on the increasing of storage capacity by rainwater storage or favoring natural retention using natural-based solution. Finally, we can exploit unconventional water resources such as rainwater, greywater, or by treated wastewater reuse, which would be the core of this presentation. The third example of circular water management could be the combined reuse of rainwater and greywater. Indeed, rain could be catched by a proper catchment surface, then sent to dedicated treatment system, such as filtration or disinfection, and collected in a dedicated tank. The same could be done from greywater. It is the drain of washing machine, sink, or shower. And these streams could be pumped again in the water cycle for toilet flushing or green irrigation. Another example of rainwater and greywater reuse could be separated reuse, in which rainwater is exploited for green irrigation and greywater for toilet flushing, obviously after dedicated treatments or filtration and disinfection. The economical evaluation of this system should be coupled with the environmental value of this practice. In other words, this is a virtuous practice, but it is also an expensive practice. So it should be carefully evaluated. Coming to the other unconventional stream, one of the most interesting solutions for circular water management is represented by treated wastewater, also called reclaimed water. That is the water coming from municipal wastewater treatment plants, which could be reused for different purposes with several benefits. For example, the access to critical water, ecological restoration, improved water quality, reliable water supply, social and economical benefits. Regarding wastewater reuse, I'm curious of what do you think about the needs which could be satisfied by treated wastewater reuse? So which of these needs could be satisfied by reclaimed water reuse? Crop irrigation, water supply, public irrigation, all of this.
So again, for participants, you can see the question and the option on the screen. Again, it is multiple choice, so you can choose more than one answer. And again, please do not forget to submit your answer by clicking on the blue button down below. Take your time for voting. Few more seconds for everyone to make their mind, and we can see the answers. So what do you think about it?
In this case, all the answers were correct, as crop irrigation, ornamental fountain supply, and public green irrigation are all examples of treated wastewater reuse, but they are not the only ones. Indeed, the concept is to reuse treated wastewater for different areas and purposes. Wastewater are usually treated in wastewater treatment plants through high economical and technical efforts and originated treated wastewater, which are commonly sent to drain and discharged in the linear way. In the circular idea, on the contrary, treated wastewater could be reused in different areas, rural areas for agriculture, urban areas or industrial areas, being again part of the water cycle, as you can see in this image. More in detail, let's examine the different opportunities of reusing treated wastewater. First of all, they can be utilized in agriculture for irrigation of crops for human nutrition, of crops for animal nutrition, crops for energy production, or irrigation of green areas, lawns, gardens, or irrigation of sport areas, for example, golf course. We can make a civil use of treated wastewater for street washing, heating system, or ornamental fountains. Finally, we can make an industrial use of treated wastewater in fire protection system or as a fluid for process cooling or heating system. These are all examples of uses in which treated wastewater could substitute totally or partly drinkable wastewater, so reducing the exploitation of this important resource. Besides the technical aspect and the strategic part, also the regulatory issue plays an important role. Indeed, the 741 regulation, European regulation of 2020, defines the minimum quality requirements for agricultural wastewater reuse. It individuates 4 quality classes based on chemical and physical parameters for water quality. It also specifies the different kinds of agricultural uses, so different crops, and individuates different irrigation techniques. Moreover, it underlines the monitoring of chemical and microbiological parameters, which are listed in the table below. Okay, you may say, okay, there is the theoretical and regulative aspect. What about the practice? So I am showing you a case study of wastewater reuse in the idea of thinking of a wastewater treatment plant as a biorefinery. So in the last years, at the Laboratory for Technologies of Water and Wastewater, we carried out an experimental project in which our aim were the monitoring of wastewater quality, the reuse of treated wastewater in agriculture, and also the valorization of municipal sewage sludge. In this project, at an Italian wastewater treatment plant based in the Emilia-Romagna region, we performed a continuous online and real-time monitoring of wastewater quality by specific probes for the monitoring of chemical and also microbiological parameters. Then we carried out agronomical pot experiments for crop cultivation, particularly tomatoes and peach, through the use of reclaimed water. In this way, we realized water saving through a water supply which was according to the irrigation needs of the selected crop and season, so avoiding any waste. And we also realized a chemical fertilizer use reduction by fertilizer dosage, which was according to the element concentration in treated wastewater with the practice of fertigation. As you can see, also water also contains nutrients such as nitrogen, phosphorus, and potassium, which were not wasted in this way. So we realized both the saving of water and nutrients. After hearing of this experiment, I want to know if you are willing to consume crops irrigated with treated wastewater. You can say yes, absolutely, only after cooking, only if they were cheaper, or you can say that you are not convinced of this practice. I say yes.
So, dear participants, you can choose your answer as well, and click on the submit button down below after you choose your answer. I feel like it's very personal, this question, so I'm very excited to see the results. So a few more seconds. After everyone is voting, okay, now we can see the results.
Okay, the majority of the answer, I said they are positive, but in any case, I hope that your idea is to be willing to consume crops irrigated. For the one who answered only after cooking, I suggest to read the regulation which imposes a higher water quality for crops which will be eaten without cooking, and another quality level for crops which will be consumed after cooking. So the regulation is in the idea of safety for users. So coming to the final remarks, what we learned in this presentation. First of all, water scarcity and drought should be considered ordinary conditions due to the effects of climate change. Treated wastewater, rainwater, and greywater could represent new non-conventional water resources in the view of circular economy. Wastewater treatment plants, as an example, must be rethought as factory for the recovery of water and nutrients in a biorefinery perspective. The safety of wastewater use practices could be granted only by careful monitoring of microbiological and chemical parameters, such as emerging contaminants and microplastics, as you can heard in the following presentation of my colleague. In this way, I concluded my presentation. I just want to thank all the colleagues which made possible this work, and of course, all of you for your attention. Thank you.
Thank you, Luigi, for that insightful overview of water stress. It was very interesting to see the potential for reusing the treated wastewater in agriculture and so on. So, as you mentioned, the safety of reusing this water really needs some monitoring and so on. So that's why we have also our second speaker. So now let me invite to floor our second speaker, Mrs. Roberta. So please, the floor is yours. Share your screen, and we are very excited to see your presentation.
Okay. Do you see the presentation?
Yes, we can see the presentation, but please run. Okay, now it is also in the presentation mode. Thank you.
In the presentation mode, okay. Good morning. Thank you, Susanna. Good morning. Thank you all for joining this NiCE seminar on the opportunities and challenges for circular water management in urban and rural areas. This presentation is focused on microplastic and emerging micropollutants on the monitoring approaches for a safe water reuse. As mentioned before by Luigi Sciubba, the previous speaker, we are part of the laboratory for the circular management of water and wastewater reuse. And in this context, we are monitoring different kinds of emerging compounds, such as microplastics, additive, and other emerging compounds. In particular, we are developing and implement sampling and analytical methodologies for the monitoring, and also we are testing the different technologies on the bench and also pilot scale for their removal. Here we have the first question for you. And the question is, in your opinion, which of the following categories are considered emerging contaminants? You can choose.
So again, please choose your answers. It is multiple choice questions, so you have more than just one vote, and then submit the answer by clicking on the blue button below. We will wait a few seconds for everyone to vote. It takes time to read all the options and think about it properly. A few more votings. and then we will share the results on the screen. So now you can see the results. Roberta, is this to you?
Okay, it's only one, the correct answer, and the number 2 is the right answer. Endocrine disruptor, and in this case, synthetic hormone. In fact, endocrine disruptors are substances that once reach the environment may interfere with the hormonal system. I give you the example of the feminization in the fish population and the collapse of the population in the freshwater environment. These classes of contaminants belong to the wide class of emerging contaminants, in which we can find microplastic, industrial chemical, also endocrine disruptors, pharmaceutical, and also contaminant of natural origin. We deal in this presentation with microplastic. Microplastic may be defined as any type of plastic fragment composed of polymer and additive with a diameter between 1 micron and 2 millimeter. Microplastic may be divided in primary and secondary. Primary if are intentionally produced into micro dimension, and the secondary if derived from the degradation of big fragment released in the environment. Emerging micropollutants are also synthetic substances that present in trace in water and also in other environmental matrices. May be newly synthesized or already known, but that represent a risk for the ecosystem and human health. And for this compound, there are no legal limits, and we need more studies to understand the risk linked to exposure to these substances. Given the potential risk of this compound, the interest in microplastic and emerging contaminant removals and growth at EU level, I'd like to mention only this European Green Deal that aim to reduce air, water, and soil pollution. European Green Deal is implemented to the Zero Pollution Action, which provide for the updating of the list of pollutants, in which we find microplastic and different classes of emerging contaminant. New restriction on the use of plastics, for example, the reducing of microplastic released into the environment, and also it reports the need of radically revise the legislation of for wastewater management. Also, I'd like to mention the water resilient strategy. There is an action plan that ensure clean and safe, accessible water, and paying particular attention on the emerging contaminant, and in particular to the classes of PFAS compound. All the regulatory action are part of the One Health perspective that recognizes the interdependence between environmental integrity, the water security, and also the population health. And important innovation have also been introduced in the regulation governing the wastewater and their reuse. As mentioned by Luigi, in the regulation 7041 are established minimum reference parameter for the reuse of the reclaimed water, but also specify that additional requirement can be applied for potentially hazardous substances, including microplastic and emerging contaminant. It's important to to report also the new directive for urban wastewater treatment that set the rule for urban wastewater reuse and treated water, and it also reports the need of the monitoring and the remove new pollutant. In particular, for organic micropollutant, it's important the application of a quaternary treatment for the abatement of organic micropollutant. In particular, this treatment must be concerned 7 of the molecules reported in the table in the right of this slide, and it must allow for 80% removal of these target molecules. Regarding microplastic, we need to research it in water and sludge in different kind of wastewater treatment plant and in the overflow discharged due to violet rays. But how do microplastic and emerging contaminants enter into the environment? So the terrestrial ecosystem are the major pathway of microplastic and emerging contaminant into the environment. In particular, wastewater treatment plants are one of the main route of abatement, but also of emission. In fact, we can see that all these micropollutant that is derived from human activities are collected in the sewer, and then from domestic and industrial discharges, and then they arrive to wastewater treatment plant. Here, wastewater are treated.
So we are sorry, it seems that Roberta has some issues with the internet connection. Hopefully she will come back as soon as possible, so we will just wait.
Of this new micropollutant. This technology is not so specific for their removal, and so a part of this contaminant may reach the environment through the water, but also through the reuse of the sludge in agriculture. It is so necessary to develop new treatment more specific for these substances. Let me know only an example of what's happened when wastewater reach the environment. These contaminants are very persistent for a long time and can be transported for a long distance. In the case of water-soil plant continuum, depending on the chemical-physical characteristic and on the composition of the soil, micropollutant follow several pathways. For example, may be absorbed on the soil particles, or can migrate to deeper layer and reach the aquifer, may be degraded via abiotic and abiotic processes, but also can uptake through the roots or leaves and enter into the vegetal tissue and accumulate in the plant. I give you the example of one molecule called carbamazepine. Carbamazepine is an anticonvulsivant used for the treatment of the epilepsy. And this molecule is really more hydrophilic and can translocate into the green tissue of the vegetable, for example, of the basilic leaf, and may be accumulated, and the risk is linked to the bioaccumulation, and they may reach the human the chain, and then impact on the risk on the human health. It's important to stress that reusing treated wastewater help address water scarcity, especially in water scarce region. But proper monitoring and management are needed for a safe use of this kind of water. In this context, our laboratory are developing a monitoring plan for the identification of microplastic and emerging contaminants. Regarding microplastic, we conduce site inspection to selected plant Then identify the sampling point, define volumes, quantity of sample to catch, and then prepare the sampling method for water and sludge sampling. Regarding the sampling, waterline sampling, we have developed a sampling system all in stainless steel. We catch water with a bucket, and then we filter the water to a pile of 5 sieves and recover the solid substances for the microplastic analysis. These sieves are on a tank that is in which we catch the water for the analysis of emerging micropollutant. This sampling system will be upgraded thanks to the project Intake for Water that is currently underway. Regarding the sludge line sampling, we also catch fresh sludge from a thickening tank, or thickening mixed sludge, a mix of primary and secondary sludge used for anaerobic digestion, for example. Once we are in laboratory, the samples are pre-treated. The samples are recovered from the sieve in a stainless tray with water or compressed air. All the substances filtered are recovered on a filter, and filters are subjected to oxidative attack for the digestion of organic material. Generally, we use hydrogen peroxide or sulfuric acid. It depends on the composition of the sample. After the oxidative process, we filter again the material and recover on a filter in aluminum oxide for qualitative analysis. First one, we analyze the sample with a stereomicroscope. Is a non-destructive analysis. Non-destructive analysis that allows estimation of the material of interest. This technique is really performant, but we have to pay attention to the overestimates because do not distinguish between natural and synthetic material. After this, the samples are analyzed with an integrated system for IR microscopy and a TRFT spectrometer that analyze all particles and identify the polymeric composition of each compound. Here we have the second question, is regarding the packaging. Which type of plastic is most commonly used to produce beverage bottle sold in supermarket? In your opinion, PVC, PET, HDPE, PP.
Okay, so now please be aware, only one correct answer, so choose yours and then submit by clicking on the blue button down below. We will wait for everyone to vote. Really tough question. Very professional one. So now we can see the answers on the screen. So Roberta, is it correct or totally not correct?
It's correct. It's correct. PET. Okay, let me show you the correct answer. Okay. Okay, PET. As you can see, PET is the plastic used for produce water bottle. Is one of the plastic found in our sample. All type of plastic polymers used for food packaging are found in the environment in the form of microplastic. In fact, in our sample, we have found different plastic with different composition, with also PET, and we have found also different shape shape, plastic with different shape, such as fragments, microbeds, fibers, and particles. Microfibers are generally the most frequently sampled type in our sample. I report in this slide some of the results obtained after processing the data. First, we compare the concentration at the inlet of the microplastic, at the inlet, at the outlet of the wastewater treatment plant analyzed. And as you can see, the microplastics at the outlet generally are lower than those at the inlet. Then we conduce a study on the removal efficiency. In particular, we test different technologies for the abatement of microplastics, and generally plants with more advanced treatment release less microplastics. We also conduce a test on the seasonality of microplastic inside in wastewater treatment plants using a different sample captured in different season of the year. Here I report the result of the polymeric analysis with FTIR. As you can see, the spectrum, IR spectrum made it possible to identify chemically composition of microplastic present in the sample and may discriminate them from particles and fiber of natural origin. As example, I report you microbeds in polystyrene. Then you can see a fiber, white fiber, in polyamide. And also I show you a fragment from a sample of sludge. And in this case, the polymer identified is the polyethylene. All the spectrum of the spectrum are compared with the spectrum in the library of the instrument to match the polymer, to match the correct polymer. Here we have the third question, and the question is, which of the following microplastic are primary microplastic? Here we have multiple choice.
Yes, so again, please, dear participants, choose your answers, more than one. Think wisely which one could be correct. And submit your answer by clicking on the blue button down below once again. A little bit more of waiting for everyone to vote. Few more seconds, and now we can see the results on the screen.
Okay. Okay, the two correct answer was microbeds and pellets. Microbed and pellets, in fact, are produced in micro dimension, not derived from the fragmentation of a big plastic. Okay, it's important to know the origin of the contamination. It's important to identify primary and secondary ones. Okay, let's us move to talk about energy contaminant. In this case, our laboratory have developed a protocol for the identification of different energy compound. This protocol briefly is start with the pre-concentration of the filtered sample and on SPE cartridge. Then the concentrated sample are analyzed in different way depending on the characteristic of the contaminant. We can use gas chromatography, for example, for a plasticizer like bisphenol and phthalate. or liquid chromatography for the analysis of other compounds, pharmaceutical one, and also for the bisphenol. These methodologies are used to identify and quantify the emerging contaminant in the wastewater, but also to test the different technologies that we are used for test the removal of this contaminant from the water. Here we have my last question, and is related to the quaternary treatment. And the question is, what is meant by quaternary treatment in wastewater treatment plant? Basic primary operation used to remove coarse solid before primary sedimentation, conventional biological process aimed at removing organic load, technique used exclusively for final disinfection through chlorination, or advanced processes installed after secondary and tertiary treatment designed to remove micropollutants.
So since this is a longer question and longer answer,
yes,
take your time, everyone, to really go through the options wisely. And again, submit your answer by clicking on the blue button down below after you are able to choose from those long answers. Okay, now we can see the results on the screen. So almost everyone voted for the last option.
Okay. The right answer is the fourth. Advanced process installed after secondary and tertiary treatment to remove micropollutants. This treatment it's consent to remove organic micropollutant that may reach the environment and contaminate different matrices and also pose risk to the human health. Among the most consolidated and studied solution for abatement, we can mention ozonization, in which we use ozone to chemical oxidize organic compound. It can destroy over 90% of many micropollutants. Another good treatment is the use of activated carbon. Carbon capture contaminants is a porous material, is one of the simplest and the most economically viable technique for high quality water. We also mention advanced oxidation process. Advanced oxidation process combine different technologies such as ozone and hydrogen peroxide, or with UV radiation. They generate radicals and are extremely reactive and degrade almost any organic pollutant. And another is the membrane filtration, is a technique, for example, like nanofiltration and reverse osmosis, act as a physical and chemical barrier to retain very small particle. This is particularly used for the removal of the microplastics. In our laboratory, we are evaluating and optimizate the UV treatment test. We are conducting testing on different compounds such as plasticizer, bisphenol A and phthalate, and different pharmaceutical compound, carbamazepine, diclofenac, and clarithromycin. We, for example, treat solution for a fixed time for 40 minutes, and we have periodic sampling to identify the kinetics of reaction and the percentage of remotion. As you can see from this slide, the diclofenac is the more removed. The removal is a measure of 99%. Also, bisphenol have a good rate of removal, 62%. Clarithromycin and carbamazepina are not so well removed with UV treatment. And so for this kind of molecules are need to test other kind of treatment. For this purpose, we are developing a system, an integrated system with 3 modules, one ozone destructor, one UV lamp, and one activated carbon. This module will be act individually, tested individually, but also coupled to define the best solution for different type of micropollutant. In this prototype is at Brasimone, our center of research where we have other laboratories. In conclusion, we can say that integrating the wastewater reuse with effective monitoring and advanced treatment is essential to protect ecosystem and also ensure safe agricultural practice, for example, and build resilient water system for the future. In this context, we surely continue to conduce monitoring on microplastic and on emerging micropollutant. Regarding microplastic, we continue with monitoring campaign and also expanding sample point and the number of the sample. We also take average daily sampling and test a new sampler after upgrade, and we'd like to characterize that as the sludge line. For emerging micropollutant, we surely develop other analytical method with the new instrumentation, and we test new technologies for test the efficiency of the removal of this kind of contaminant. Okay, thank you all for your attention. You can find my mail, and thank you.
Thank you, Roberta, for everything that you mentioned for this technical complexity. But as everyone knows, it is also important what we do at home and in our city centers. And for this purpose, we have our final speaker, Mrs. Cortesi, and she will present the Bologna pilot, the water kit. So, Sara, the floor is yours. Please share your screen and conclude what is practical for citizens.
Yeah, thank you, Susanna. Just a message for you and Lucia, since we are definitely running late, I will skip the poll in my presentation so that we can save a few minutes, and I will try to go as quick as possible. And thank you, Lucia. And I thank also the attendees for their patience. If they want to stay with us, we will finish in, I think, a quarter of hour, and probably will also have in that quarter of hour the time to answer possible questions. So here we are. I'm sharing my screen. I'm Sara Cortesi. As Susanna said, I work for ENEA as well as the colleagues who preceded me. We work in the same sustainability department, in the same division, but actually I belong to a different work unit, which is the Laboratory for Sustainability and Circularity Tools. I am, and I will be for a few more months until the end of the project, the project manager, the contact person for ENEA for the NiCE project, which is this European funded project funded by the Interreg Central Europe program of the European Union, which has this overall goal of promoting sustainable and circular lifestyles, particularly in city centers, and support citizens in their day-by-day choices and activities in order for them to be able to live a more sustainable and circular life, to produce and consume in more sustainable and circular ways. there were different Central Europe nations involved in the NiCE project, and each partner, each nation decided to work with one city. And so we have 8 cities involved in the project for Italy. And so for ENEA, which is the Italian partner of the NiCE project, we decided to work with Bologna, which is actually also one of the locations of ENEA in Italy. And it is also the location where Luigi, Roberta, and I work. Those cities were paired, were twinned, and worked in tandem. So, for example, for Bologna, we worked with our colleagues of the University of Economy and Technology in Budapest, in Hungary. And each one of the cities decided a specific topic on which to apply that general and implement activities in line with that general goal of the NiCE project. For Bologna, the selected topic was actually water, and this was because water is an important topic for cities like Bologna, who are basically facing the two extremes of the problem. That is to say that we have water scarcity during hot summers, and since the temperatures are rising, this problem is bigger and bigger. And on the other side, we face more and more exceptional weather conditions, such as floods, which affects the lives of people, the infrastructures of the city, the commercial and businesses located in cities like Bologna. So we focused on circular water management, and we based the activities definitely on the strong knowledge and skills presented by my colleagues in the 2 previous presentations, but we didn't work only with technicians and researchers, but tried to involve individuals, so citizens or group of citizens, civil society associations, and closely worked with local public authorities, such as, for example, the Bologna municipality, which is actually also an associated partner of NiCE, meaning key supporter, key external supporter for this project in Italy. So we experimented with circular water management in 2 different ways. One was organizing a urban living lab, which is an experiment which ran for almost 1 year, from summer, autumn 2024 to the end of the spring of 2025. And in the urban living lab, we engaged citizens in designing, building, and testing together systems for the efficient and circular use of water, especially for urban farming. So to understand circular water management in relation to growing plants, vegetables in a urban context. On the other hand, we had a school living lab, meaning that especially my colleagues worked with primary, elementary and middle schools in the city, so with teachers and students to discuss with them about this topic and to experiment with them ways to save and reuse water daily at home with their families and their friends. So we did this pilot project. Obviously, ENEA originated the project and also was the focal point of the activity. But actually, this was possible only through the activation or the connection to a very diverse ecosystem of stakeholders working together. So we involved, as I said, the Bologna municipality, but actually also neighboring municipalities were interested and were actively participating participating in the activities, also with a look to possible replication of the same approach and same activities. We also had on board, as I said, civil societies, so many NGOs and group of citizens, as well as individuals. We were supported by a university startup focusing on water and out-of-soil cultivation. Schools were important, universities were important, and also in our stakeholder group, we also had the water and wastewater management company, which is obviously a key actor in the circular water management topic. So from our competencies, our previous experiences, but also from the experiences that all partners grow during the realization of the pilots, we produced a few handbooks, manuals, tools that constitute what is called the NiCE solution box on different topics which reflect the topics faced in the cities involved in the NiCE project. From the Bologna experience, we produced the Circular Water Kit, which is a handbook on how to use water in a circular way in the city. The main two targets of this handbook are, on one side, individuals, so the citizens of urban areas, and on the other side, the local government of the municipalities and policymakers for the cities. You can find the Circular Water Kit on the NiCE Knowledge platform, which has different sections with lots of resources related to the project topics. And in the resources section, you can find the different elements of the solution box, among which the Circular Water Kit, as well as other documents and tips and so on to improve your knowledge about the NiCE topics. The main goals of this Circular Water Kit, which was developed by ENEA with our twin partner, our tandem partner, which is the University in Budapest in Hungary. Main goals were to support the adoption of water use practices and promoting basically sustainable water management, to raise awareness at different levels. As you saw, we have two main targets, but obviously this is an important topic for many different actors that can contribute to make water management more or less sustainable and circular, but also to offer practical recommendation and tools and knowledge to start tomorrow the path towards circular water management at city level or at home level, as you will see. So for local authorities, urban planners, we provided steps to integrate water saving and water reuse, which are two different things, as also Luigi mentioned, but very intertwined and fundamental to promote circular water management. And those steps start by assessing water needs and local water resources by doing different actions, which are detailed in the document, and then developing a water saving and water reuse strategy, starting from vision and strategic objectives up to identifying financial and economic resources for the envisaged strategy. Then again, for local authorities, we have in the document policy recommendations. For example, type of policies which can support circular water management, but also examples of solutions, regulations, tools adopted by other cities in the real world, across the world. for example, in Singapore or in the US, but also in Europe, as well as in Australia, or in remote islands that obviously have their own specific context and way of dealing with this kind of things. Lastly, for local authorities, we provide, and this is a link with the other part of the document, tips, suggestions, direction on how to improve community involvement and public awareness. So from organizing educational campaigns to collaborating with local organizations and stakeholders, the ecosystem that I showed you before, as well as strategies to build trust and encourage citizen participation. You saw the question Luigi asked about will you trust vegetables raised, grown with this kind of water? This is part of the problem. Being aware at different levels. No, we do not want to everyone to have the technical and scientific knowledge that my colleagues presented, but everyone has to be aware of the effects in order to decide what to do and how to contribute to this action. For citizens, we have a collection of very practical measures to save water at home or to reuse domestic water. And they are based on the outcome of the Bologna pilot, but also on the 20 tips for saving water and also energy, which is the other side of the story, developed in recent years by ENEA. Okay, so as I said, I will skip these poll questions in order to go quickly towards the end. And we also have a collection, and this is coming from, again, from previous experiences, but a lot from what was done, especially during the Urban Living Lab in the Bologna pilot. We have a collection of solutions for outdoor and garden water management. For example, we talk about rainwater tanks with phytoremediation, which was one of the solutions applied during the Bologna pilot, as it was hydroponic cultivation towers, so a way to reduce space as well as water needed to cultivate vegetables or herbs or decorative plants, also in small spaces such as those often available to citizens in city centers. And we talk about and describe what is a wicking bed, that is basically a raised growing bed with a water collection tank under the soil, again, allowing an efficient and reduced use of water, as well as reusing water coming from like rainwater or collected water, which can be used by the soil when it's needed. So in the end, the Circular Water Kit for us is a tool that we propose as a manual for education, definitely. So also for schools at different levels can be interesting to have it and to use it for planning. So for starting planning in small, medium, and even larger cities which have not yet started to face this problem, which will become more and more common for all kinds of cities, and definitely to take action. As I said, from tomorrow you can do some of the things that are described in the kit and drastically reduce the use of water as a citizen or a group of citizens within an area. It combines, as I said, there are technical parts, definitely, but it also involves behavioral change, which we know is definitely important for our journey towards sustainability and circularity. And again, since one of the main targets is local authorities, municipalities, and urban planners, governance is another important aspect. If you have questions, I think that our colleagues from Slovakia will collect them now and share it with us. You can also contact us. You saw our contact info at the end of our presentations. This is mine, so please feel free to contact us about the water management topic, as well as more in general about the NiCE project, whose final conference will be in Germany in mid-March. So please check the NiCE project website for more info about that. Thank you so much.
Thank you, Sarah. It was very inspiring to see how the circular water kit really easily translates those, I don't know, complex water strategies into very simple tips, how everyone can save water and energy. So I hope that by this conclusion, we really covered the whole circle for the water today. So thank you everyone for your participations. As Sarah mentioned, if you have any questions, feel free to share them with us via emails, which you can find on the NiCE website. And then please expect also the participation certificate, which we will share with you. And if anyone wishes, you can find the recording of this session also on the YouTube as soon as possible. So thank you again. Thank you, dear speakers, for your very inspiring presentations. And I hope that we will see each other somewhere else soon. So thank you, everyone. Goodbye.
Thank you.
Thank you. Thank you, everyone.
Thank you. Goodbye.
Goodbye.
Bye.
Goodbye.